Okay, so the topic of the talk is reducing query time up to 60%. It's not flat 60% with selective search. So I'm going to start with introducing myself and then agenda. So I am Rajani. I work for Lucidworks as a search consultant for professional services team. I've been in this area of search, machine learning for years now, I think 10 years. I started back in 2008, and it's been since then till now. I've been working with various customers. I started with pharmaceuticals and banking, e-commerce, and right now, mostly so many Lucidworks customers that it's enterprise, it's sort of large-scale search companies as well. Back in 2016, I did my master's at San Francisco State University, and my advisor was Professor Kulkarni. So this work was almost under her supervision. It's her research paper, and she had done her research back in 2003. So this concept comes from that time, and she did her PhD. What I did as a part of my master's was just kind of implementing these in the latest technologies, like using open source Apache Solr and Apache Spark. So let's see what it is about in the following slides. So the agenda is I'm going to give a brief introduction to what I mean by large data set search applications, and then the current implementation of such applications and the shortfalls, followed by research implementation, the experimental setup and results, and finally conclusions. Not much about related to conclusions, but for sure experiment sets and details, and then you should be able to tell me what conclusions would you derive out of it. Okay, so what I mean by large data set search applications are those applications that have data in size of terabytes. Like if you have millions of documents, then it's not really a challenge to manage. You can host some 2 or 3 shards, and then you can get over the implementation. But now if your data is always growing in size, and it goes to 500 millions, and then it goes above that, then having that many number of shards and then serving search requests is just that you need a lot of computation resources. So as your computation resources need grows, then it also kind of comes with cost. So you want to make sure that you're serving search not by adding a lot of resources, but still kind of like doing it with the resources that you have. So that's the main idea here. So I'm talking about those kind of search applications. Could be like publishing domain, like clinical research domain, some enterprise search domain, where your data, like enterprise search, will have always new articles coming in, and then they never go away. So the data keeps growing. So such kind of application I'm talking about. Also making sure that the search is swift in the sense like the way Google does. That's the best example we always have. Okay, so the current implementation, the implementation that I'm talking about is mostly Solr, but should apply to Elastic as well. The one that I have done as Solr, that's why it's kind of the terminologies that I use is mostly Solr. Okay. So the current implementation is usually you have the data set, and what you do is you then have a Solr cloud here, and you start ingesting. When you start ingesting, if you do a default ingestion, what Solr does is it chooses the composite routing strategy. That is, it hashes each document that comes in and distributes across the shard to make sure there's a balance between the document's distribution in the shard. So that's how the documents get divided into shards. And at the query time, what you do is you search across all the shards. Whatever is your user search request, it has to go across all the shards and then get back the results for you. So it's really computing here, all the shards, and then getting back. So you need to make sure that your shards are good, or with good computing resources. It's not and available all the time and capable enough to meet the query per second rate, right? So that's about the current implementation. And though that implementation is still working, I have worked with so many customers who had like terabytes of data, and this had some 36 shards, 50 shards, and they have been able to get the system working. It's just about the challenge of having that much of resources. But then if you can afford for 50 shards, then good. Also at the query time. So the shortfall of that implementation is, like I said, the cost that is incurred to search exhaustively across every partition of the collection. So you search across all these partitions or shards, like I'm using synonymously. So you got to search across all of these shards. So the challenge is you either make sure that you have a lot of computation resources so that your query is the query performance is good, or if you try to put the number of shards in the same node, then your query performance is impacted, right? So if you overload your shard, then also your query performance is impacted. So the research implementation here is dividing the same shards, not in a way that it just balances and randomly distributes the documents across the shards, but trying to divide the collection into subject topic shards. That way, you know that each shard has specific kind of a topic, subject related documents in it. So that's the idea here. So the motivation is to avoid these exhaustive search that I showed here in this slide. Instead of doing the search across all the shards, that's what I call as exhaustive versus selective. So we try to search across fewer shards in the research implementation, so that we avoid that computation cost required per shard for the exhaustive search. So the concept is we know that the documents that we have in our collection are kind of related. They are not really unknown documents. There is some relationship between the millions of documents that we have. So why not organize those documents in a way that the related documents are concentrated in the same shard instead of having them distributed, so then you have to search across all the shards. So that's in academics and also in the theory, the concept is named as cluster hypothesis. So if you see the moment you have documents, try to organize documents that are related, you see that the cluster formation, these are related documents that are close to each other. I'll talk in detail in a few further slides. So here I'm just trying to relate the concept that I'm focusing on, that is dividing this collection into subject shards instead of the shards that have randomly distributed documents in them. And how I cluster those documents is based on the relevancy in the information, the content of the document. So the literature review is, like I mentioned, Kulkarni and Callan, Jamie, both are professors from Carnegie Mellon University who has done research on this, known as selective search. In this slide, I just want to give you a view of the word cloud after distributing the related documents in each shard. So let me see if I already, I opened it for the talk. I don't think this will be, this is the screenshot from after I indexed, I ran the clustering computation and then projected those documents. And you see, these are the words, top terms picked from that shard. So the cluster 4 is nothing but shard 4. The cluster 5 is shard 5. So this is just a screenshot, but if you see, this data set is the 20 news group. If you are aware of that, that's one of the standard data set. So the word subject is just because every document has subject, and we could remove that as a stop word, but I haven't done it just to make some relationship between the documents. So you see, this one of these cluster can you see what's, is it kind of visible? Yeah, okay. This one was one of the clusters which had documents related to religion. So you see all of them are like God, Christian. These are like stop words that I had to remove, but yeah, we have a stop list word that you can filter out. So, but you can see that this cluster has all those related documents which has those terms. Similarly, if you see this one is also a similar but different topic. Let me just go for the politics one. So you can see that pattern where after the clustering job is run, you see similar documents are concentrated in the same in each shard. Let me go to some other clusters. This one is science cryptography. So you see those words. If you see those words, you should be able to tell, okay, this is a cluster that has something related to science. And then if you go further, you see sports related, that's baseball, like league, those top terms that we usually use in sports. Similarly, it has 20 topics. The 20 news groups has 20 topics. So the cluster itself, so the documents itself was divided into 20 shards. It's just for making sure that the clustering is working well. This one is related to electronics. So you see there is some electronics phone kind of device and all that words here. This one is interesting. This is one of the data set uploaded on the Kaggle, I think from one of the career builder or someone who has uploaded the jobs posts, so number of job posts. And you see this one is jobs related. It's basically clustering on job description. So if you wanted to kind of like make your job site to suggest the jobs that are related, then you query on the same shard that has that kind of topic, then you get more relevant documents instead of just going through all of them and then trying to improve your relevancy by exhaustively searching across all shards. So that's the idea. Here, if you see your cluster, your shard itself has already related documents. The lawyer and all of them related here. This one I think we are very familiar with, like management, development, software. There was one software related I had. Yeah, this one. So you see software developer, company, developers, position, Java. So imagine if you had two positions, one as Java developer and one other as a code ninja. Both of them are actually asking for Java developers, but then they're just different terminology. And now you wanted to suggest a user that, okay, when you're searching for Java developer, there is also a person by Code Ninja as a title, then you could potentially get those documents from this cluster because they are all then related documents from here. So you also improve your relevancy. Okay, so going back to the talk, so that's what I wanted to show, that once you try to group similar documents in your collection into a shard, then you see that they're all related documents concentrated on the same shard. So these were the two data sets, a few other as well that I experimented with to make sure that the concept that we talked about, that's cluster hypothesis, is actually true, which we could see that in the cluster results. Okay, so digging detail into the research implementation. So what let me kind of put it in the present mode, and maybe, is it visible? Okay, so the difference between the current implementation and research implementation is this. So this part here just down, what I'm trying to do is build a model, like a cluster model, by using some percentage of data set. So if you already have some data set that has category tagging on it, then we could actually get those, let's say, a percentage of data set from each category, and then build a model based on those categorical documents. That way we have now a trained model which can actually tell the future documents that are coming belongs to a certain shard. So that's the idea. But if we don't have that kind of data set which has some categorical differences, showing the differences between each category, we can still go by random sampling. I have done both the experiments. I'll show the results in a bit. So there are two ways. One, you do random sampling. The other way, you could just say, oh, I know this percentage of data set belongs to this category. So I build a model based on these many categories. That way, the model is now learned enough to know which shard that it should pass the document to. So here, now once you have the model ready, you use the model to then post the document to the shards. Now you're not anymore using a composite routing. If you are aware in Solr, or if you have ever done these kind of source origin documents pushed into Solr, then you use implicit routing. So that's the one that I have used here. Now I use the model to predict which shard this document belongs to, and then use the implicit routing to route to that specific shard instead of using the murmur hash or some other techniques. So extra computation is to create this model, but then once you have the model, the routing is just same as how you would compute a hash. You're just going to predict which shard it belongs to, and then you just pass the document to that shard. Now, since the model is able to tell that, okay, this document could belong to this shard, so now you can imagine that these all are topic shards. That's similar to the way we saw in the word cloud. So this is an additional piece here, which you do offline. We usually are building such models every day lately. And then at the query time, now because you have all these shards that have related documents in the place, you don't want to just go and do a exhaustive search. So what you're going to do is have some selective search algorithms here to then pick only fewer number of shards instead of all the shards. So like I said, this works for the kind of implementation where you have data in scale, not really in 10 million or 5 million, where you can just say, I can still go ahead and search for across shards. It's for like 20 shards, 50 shards, where then the computation research should be good to make sure that it meets the query time. That's when, that's when you need kind of such implementation. So I'll talk a little more about what selective search algorithms are. They are not expensive algorithms. They still also, my experiment results prove that those algorithms still don't take much time as compared to the exhaustive search. So in the implementation, I talked about the clustering algorithms. So the clustering algorithms that I have tested on was k-means. So like I mentioned, you could just pick just randomly pick 5% of your data set or 10% of your data set in uniformly random, just pick the documents. Or you could just say, the second one was vocabulary-based rejection. What that means is, now you pick 5% of your data set, and all the 5% of data set will have some common terms that you actually don't want to consider them as the terms to decide which cluster the document should belong to. So you could just, when you run the k-means, before that you can say number of dimensions that you want to make use of to build the model. So you could reject some top documents to make sure that those top term frequency documents are not really the documents that are in use to build the model. And so I have experimented with these, but there are many other clustering algorithms, especially the LDA, that has been also tested and said to be performing much better than these from those research articles that researchers that I mentioned in the academics. But I have done it only till k-means, and it's still good. Also because k-mean has a good performance. And the selective search algorithms that I have used are the relevant document distribution. I'll talk about it a little bit. And then the other one is collection relevance inference. These two are also, again, the research papers and research by one of the students of those professors. So I have used two of them. There are many others. There is also a learning to rank model. So we could just, in the selective search as well, we could use a model that would then also predict which shard it should go and search against, or use the other two algorithms that I'm talking about, which are very simple. Okay, sorry. Yeah, and for Solr, I have used the implicit routing instead of the composite routing. Okay, so now getting down to the experimental setup, how did I experiment these concepts that I'm talking about? So you see there is, from the bottom up, you see there is Apache Spark cluster. It has the number of workers. I have hardware specs in next slide, but just there is a Spark cluster which has the clustering algorithm. So Spark itself has a k-mean libraries in MLlib, but that had some issues with distance algorithms. It just supports Euclidean. It does not support cosine. So I had to do some tweaks, actually extend that implementation to make sure that it does cosine distance between the documents to make sure that which shard it belongs to. So that implementation is here. It's run on the Spark. And then I've used Spark Solr libraries from Lucidworks to ingest those finally predicted documents into respective shards. And then at query time, I have a selective search algorithms implemented. It's all here in the GitHub repository that I have linked to. Yeah, it's just down in the, yeah, here. So those algorithms are now selecting top ranked shards to then pick which shard the document belongs to. So the selective search algorithms that I've been talking about, the ready, that is relevant documents estimation, how that works is you kind of now build a central index by taking that is the simplest implementation I'm talking about, where you pick, now that your topic shards already know that there are topic related subjected documents in each shard. So what you do is get some 10% of document from each shard and build a central shard index. So when you when a user query comes in, you send the query to the central sample index, which will then tell, okay, these documents are concentrated in these shards. So then you pick those just top ranked shards and then query those shards and then return back the results instead of going through all the results. So that's about the ready. And the other one is called Cori. That's collection relevant inference networks, but the name itself doesn't match the short form, but it is what is called as. What that does is it is trying to kind of do a LTR, the learning to rank, but then not really a pure LTR, where it gets the top terms from each shard and records it in a kind of, again, a central index. And then the moment you have user search, you look for those terms that are present, kind of inverted index, that will then show the mirror of these all shards. That way you know this user search terms are in these shards, so you just go to that shard. So the best example is you have, like we saw some data sets, 20 news group, you have politics related documents and you have some science related. The moment you use those words, then you know that those documents are concentrated in these shards, and so we get only related documents. So the data set that I've experimented on is 20 news group, because this has clustered documents already, so it's easy to test. And the next one is BBC. That's also another kind of news data set. The third one is what is a large scale data set, a clue web data set, that if you've been in academics, you are aware of this data set. It's almost, it has 500 million records, partial data set as well. And the last one is jobs that I showed you guys just a while ago. So the hardware specs was just 32 GB RAM, 2 nodes with the i7, and then that's the hardware specs. It's just 2 laptops at home that I've experimented back in 2016. And then Solr Cloud version was 6.2.1, also supports 7.x. The Spark cluster version was 2.0.0.0. It was standalone cluster with 1 master, allocated 2 gigabytes, and then 2 workers. Just Scala and Java, just because the Spark needs those specific versions. So that's the experimental setup that I had. And now digging into the results. So I have the ClueWeb dataset is really large, really large. I've just, to test, I've used 5 million in total. So the model was trained with k-means. If you're aware of k-means, then so the number of features that I've used is 32,000. And then the number of iteration it ran was 5 times. And the minimum document frequency is the terms that it picked on to build the vocabulary is the dictionary is 100. So any term that it picked as a potential feature was at least occurred in 100 documents. And so total time taken to pre-train this model on that hardware, on this hardware, with all the setup was 1 hour 12 minutes. So if you're already aware of building these ML models, you know that as the size of dimensions grow, the computation is expensive. And also the number of iterations increase, then also your computation is expensive. So this model that I have built and tested on was 32K is the number. When I did 50K, it was kind of having out of memory issues because of the limitation of hardware here. So it's just with 32,000 dimensions and 5 iterations. The model was developed. Now the model had that part of ClueWeb dataset, which was randomly sampled documents picked from that dataset. So after all that experiment, these are the query time results. So let me just give a brief on this table. So what I mean by query queue time is query time, Solr that Solr returns, and query is just one of the selective search algorithm. So these these number of rows are actually the queries obtained from QRLs. If you have there is a Trek eval on such kind of evaluation in information retrieval research area. I have picked those 100 queries, but in this slide I've just put some 12 queries. If you want to see the list of all the queries performance, then you could just take a look at my GitHub. You have results there. But this one is the top 12 queries that were in the QRLs. So that each query searched against, using this algorithm, searched against 10 shards. So it would pick top 10 shards, ranked shards, through this algorithm, and then search against those shards. And then also we have a qualitative analysis in the next slide. But you see the query time here. For just searching against 10 shards, it took 17 milliseconds. And then for 15 shards, it was 23. I think this is expected, but just kind of like you search for 20 shards, then it's 28. And then the ready is sort of a little expensive than this one because of the way that it does the search. So you see it's taking 10. For 10 it's 58, and 15 it's 53. This one is exhaustive search, is 391 milliseconds, and this is what we do today in current implementation. So we have to just search across all the shards. So this is then searching across all the 50 shards. This was a 50 shard setup. So it was searching 50 shards and divided into 2 nodes. If you were to divide it into 50 nodes, 50 shards versus 2 shards that versus 2 nodes that I did, then it would have maybe met the query performance rate a little better, but then that came at a cost of 50 nodes versus 2 nodes. Okay, so the first line is actually the average of all the queries that it went through, but then the others are just each query's time it took for computation, each query request. Okay. This is qualitative analysis in the sense, now I'm retrieving I'm only querying 10 shards here. I'm querying only 15 shards here versus I'm querying all the shards here. So is there a potential possibility that I may lose one of the relevant document, which is kind of not, I wouldn't say, but the result says that is not possible, because now you have organized your data in a way that they're all related documents clustered. So there's still like 5% of chances that research also says, and that my experiments also say, that if you use some sort of like word Apple, and you have some such data set where you have Apple electronics as well as Apple groceries, then there are chances that it could get kind of different results. But that usually is not possible because of the way the data is. But that 5% chances are still there. But then the related documents are always in the relevant shards. That way, what we are saying here is the qualitative analysis is against that queries that we have queries from the TrackEval on the clue web dataset, and it shows that these are the standard precision at 5, precision at 10, precision at 30. So if you run the TrackEval program after you generate your ground truth queries as well as the test queries, then you will see that this was the results that I got. So for the ready, so the precision is really 0.151 for exhaustive search. Why is it not 0.91 versus 0.15? Because of the number of queries that this was tested against. So queries itself had 2009 until 2012 number of data sets. So I have tested this only on 2009, but the queries itself are full, covering all the set of data. So the precision has come down to 0.151. So we are comparing here with exhaustive versus the selective search. So you see they are still doing good. The ready is doing good at precision 5. It's still getting those match document that we are expecting compared to the ground truth results. And so it's the same. The underlined one are showing that ready is still doing good versus query is also doing good at precision 5 and 10. That means you query only 5 shards, query number of 10 shards or 15 shards. The first 5 documents have the same precision compared to the exhaustive search. So that should then give us confidence that, okay, I group my document, shard my documents in a topic-based clustering, and then it still gives us a good results with searching against fewer shards than many shards. Okay, and then this is just to make sure that the cluster distribution is not lying. I mean, it's the experiment result. So you see this was for news group data set, and you see these are the documents that were divided into 20 shards. So there's still a balance, as well as, because the data set itself is balanced, so you could see this balance as one of the possibility. But then ClueWeb also have a similar view. This is just showing that I have 20 shards, each shard, number of documents in each shards. That's the representation. Okay, going back, and I think we saw the word cloud already. Yeah, that's the end of the presentation. These are the references. These are the research papers that I have looked up when I did this work. And just show, so it's on my GitHub, but I just wanted to show how easy it is to, sorry, I thought I opened it. All right. So this is my Git repository I'm talking about. Spent a year almost doing this work, so it should have a very good information for you guys. It has all the source code here, all the K-main implementation, the Spark libraries that I've extended is all here. I also have like the architecture, the version compatibility, and the how do you get started. Either you want to run on command line or you want to run it on Eclipse. Sorry, your IDE. I use IntelliJ. And running on Spark cluster, the command itself for the large scale, how many number of partitions, how many number of features, how you could pass that as a value, and then the setting up Solr Cloud. Also, the visualization that I did is, if you guys are aware, it's a banana dashboard of Solr. I have used that, so I have also provided some instructions on that. Some troubleshooting tips, and then references, similar references. Okay, this opened up. So those who are actually code savvy and wanted to run this, you could just spin up this, clone this project on your IntelliJ and have this BBC data set, which is I think 2,000 documents. You could download that, and I'm not sure if I can zoom this. Just wanted to show this, but let's see. This is all I could do. Is there a shortcut on IntelliJ? Top. Where is that, you said? View. At the bottom. Enter presentation mode?
Yeah, should be a bit bigger.
Oh, awesome. Thank you, Adrian. Yeah, so this is BBC k-means cluster, so it will do the entire job. So all you need to do is give the directory path where you have put all the BBC records in one single directory, and then the stop words that you want to exclude. So what it does is it basically then creates the string documents by using Spark's API. It loads and it streams the documents, and then it creates a TF of all the document, gets the term frequency of all the terms in the document, and then builds the vectors that is required for your k-mean implementation, k-mean job, and then it generates the result k-mean model here. The result is nothing but the k-mean model, which is writing to the file as a centroids. So then it's, at this point, your model is ready, and it's using the same model to then, you see there is a model used, the collection name, and then the zookeeper where you wanted these then documents to project it and index. So that's all happening here. So you could just refer to this code and run the jobs, and then you can dig in detail to see the implementation. Okay, I'm done. Thank you. Okay, questions?
Thank you for your presentation. And can you please explain again about this 10% index? Why, of what documents it should be composed, and when we use it?
So did you mean about the central index I talked about?
Yes.
Yeah? Okay. So let me quickly go to the slides, if I can take help of slides to explain that. Yeah. So you need that 20% because 10% or any n% of documents because you want to do the selective search. Now, in a current implementation, what you do is you have user search and you're searching across all the shards. Now, you want a technique, a kind of a way to limit your query against certain number of shards. But which shards? Now, your shards are all clustered, are having all relevant documents. Now, when I search, I don't want to search across all shards. That means it's same as current implementation. We are not making use of the idea that, okay, relevant documents are in relevant shards. Why not just get records from there? If you, let's say you have categorical documents, you have some categories like, let's say, mountains, let's say seas, and all that. Okay. So I think I'm done with time, but just very quickly. So you actually have to do that because you make use of the selective search implementation. It's a block in the selective search that does the job to decide which shard it should search, so that you search fewer shards instead of all of them. If you didn't have that piece, then you would have to search across all the shards. Or if you still don't want to build a central index, The only solution is, I mean, not the only, the one of the solution is you build a model on the other side as well, because you already have a trained model here. You use the same model, then you should be done. You don't have to even build a central index. But if we don't want to build the model, then it's, so yeah, if I can answer your question data later. Thank you.